So a little bit of background on me and why I think sort of relevant to this talk is my background was in physics, and then I did a tiny little bit of programming then, and then I worked in international developments, like the NGO sector with charities, and that's why I started to do a little bit more programming. But it took me years and years to find uh, strategies and ways of working that I thought made me work quicker and made some of my analysis a little bit more robust. Um, I'm still finding strategies to try and do that. But recently, as I've been working on more and more data science projects, I realized that there were patterns in terms of when I was starting a project. I was arranging a projects in the same sort of way each time, and I found this to be really useful. And um, yeah, the way I was arranging them, I thought was making it easier to sort of quickly regenerate outputs or address some of the common issues that I've had when doing analyses. So I'd say I just want to make sure you know who this talk is for, so that I'm not wasting anyone's time. I'd say this talk primarily is useful for you if you're interested in using if you're using or interested in using programming languages for research or quantitative analysis. You don't have to be using those, but I think it's more relevant if you are, or at least interested in using them. Um, and mainly, I'd say this is aimed at people you may have been coding for a little while, or you may be learning, and you may have heard of words being thrown around like best practices. You may have heard of people talking about things like testing and documentation, but not really understood what they are or where they fit or how to use them. I think that's often the case in terms of how they're sort of portrayed. It's very much talked about as something that you have to do, and there are loads of things that you have to do, but not really explained why or where and how. Sometimes it's not relevant. And then on top of that, if you're interested in making your research more open, reproducible, and robust, um, and just trying to make your own life a little bit easier, it's not. This talk is not going to be for you if you want an in-depth demo of testing frameworks or how to develop documentation. This is more of a high-level overview of some strategies that you can implement to make your work and life a bit easier. So a few caveats, the things to be aware of. You don't have to learn all of this stuff at once. I slowly implemented this stuff project by project, and it takes a while to figure out what's useful and what's not. In this talk, I'll try not to focus on tools too much, more concepts, but I give resources on tools that are out there and how to use them. And how you use these best practice approaches is really up to debate. Some people may agree, some people may disagree, and there are probably people who are more qualified than me to talk about this. But I think that is sort of the point I'm trying to communicate in this talk, is that part of adopting some best practices is a matter of learning over time and figuring out what works for you and what doesn't work, and what you might need to do more of and what's overkill. So what is, I guess, the type of issue that I commonly come across when helping others, and this is an issue that I had particularly when I was starting work in the NGO sector, as I was saying before. These slides will be shared afterwards. What I've said so far hasn't needed any sort of visual support, thankfully. So thanks, James, for stopping me before I went too far into it. But I'm hoping these slides can be shared as a resource for people to sort of know go back to and as and when they're trying to implement some of these strategies. So yeah, when I first started programming, I had projects that often looked like this, and this is something that I've seen with many people that I've supported, sometimes through JDI. So you might see a folder with multiple versions of scripts, loads of underscores for different versions and different names. And often when you see a project like this, people will complain that it is hard to maintain. So if they want to make a simple change, often they'll want to change one thing in their whole analysis pipeline. It'll break the whole sort of code base. Something like this is often hard to get running somewhere else, so it might work in your laptop. But if you get a new laptop, or if a colleague wants to run it, or you need to run it on HPC, it can be a little bit difficult. And then sometimes it's hard to understand. So imagine you go on a trip, on a holiday, or you're someone else coming and looking at this folder. When you look at it immediately, you don't straight away know where to start. I think there are a few, I'll go into them. I think there are a few strategies that you can take to make your life a lot easier. And this, I think you may have seen the email that this talk is linked to the UK Reproducibility Network group as well. And I've received some great training from them before, but I wanted to add to some of that to make it more specific to this type of coding-based research. So you can rearrange your project and use some different strategies, and that will make for some better science, more transparency, accountability, those types of things. But also, I think there's selfish reasons. So you can save your future self. It'll make it you can make it easier for future you to come back to a project and rerun code. You can speed up. You can make your project into more of a pipeline. So if you have to make one change in your code base and regenerate all your results, say for a manuscript, you can do it really quickly. You want to have more confidence in your results. So you want to know concretely that the code that you've written is doing what you expect. Increasingly, journals are requiring people to share code alongside their analysis. And it would be very difficult if you were to try and share a folder that looks like this. It'd be difficult for reviewers, but also people trying to reproduce what you do to be able to follow along and understand how this works. And also for employment opportunities, I think making a coding project like this is, if you have it online and people can see it, it's a really good way to show that you are writing good code, you can explain what you're doing, and employers can quickly see see everything that you've learned. So this is essentially the type of structure of a project that I've arrived on. So you don't have to absorb this all at once. I'm going to go through each of the sections of this folder and explain what's going on here and some of the underlying concepts linked to that. A key thing is that you don't have to do everything in this talk every time you do an analysis, but I find a lot of it is helpful for most projects, but I'll go into when and how you use it. And then I'll suggest learning materials that you can look at to follow up. So let's start the easy thing. So you've got a folder here, your project. First thing we're going to look at is you including a README. This one's quite easy. So essentially the concept here is that you have one folder containing all the work from your project, and you have one file in that folder. There's the first file that anyone should open. This file is for you in 6 months' time, going back to this analysis, trying to figure out what's going on in your project, or it's for anyone else who needs to reproduce your work. Sorry, I realize there's a spelling mistake in the slide. I'll change that before sending it out. Things you would want to include in this simple text file is a summary of the project, and this could include the status of the project, whether it's ongoing or whether it's stalled or paused. What I tend to call a quick start guide, so that is a guide that tells people who've accessed your project for the first time what are the most important files that you need to know about. If there's code in the folder, how do you, in what order should you run the different scripts, and a setup section which tells someone, oh, you've received this folder of code, what steps do you need to take to make sure that you have all the right packages and dependencies and things installed. I want to explain that in a bit more detail. 2 resources, and again, I've included the full links here in case people are taking photos of the slides, but also these slides, I'll share them around afterwards. The Turing Way is a big project run by the Alan Turing Institute that talks about making more reproducible, making research more reproducible, and they have a really good guide on these README files and what should be included in them. I've also included in the bottom there a resource to a sample README file that people use for data science projects. Okay, so you've got a folder with a README inside, which tells you the main files that you need to know about. Next, you may have noticed that I have a data folder, and within that, you've got your, say, your raw and your processed data. Now, why have I done it like this? So often what we see with projects that people bring to us is you may have a data file, you may have like a notebook or a script or something that analyzes that file, and then you have a series of outputs. But what happens as the data science project evolves is usually, I tend to think we start with an exploration phase where people are writing code to explore their data set. They may be writing more and more code to start to do the analysis. And this then goes into a growth phase where the notebook or the interactive tool that people were using to analyze their data starts to grow and grow and grow in terms of size and complexity. And then it starts to balloon to the point where it becomes really, really difficult to see exactly how the person doing the analysis got straight from data to outputs. And one thing that I've seen often before, and this was something I used to do myself, so I'm just trying to get this window out of the way for me, is you tend to see, say, a data file that gets processed, and then there's a script, say, called clean data, which then rewrites the data file, changing it, and then you have an analysis and some outputs. And then the issue that you often see is next someone tries to rerun their analysis again, but the original data file they've actually overwritten and changed, and so say the original cleaning script may not work, or may produce different results than people expected, and then when you conduct your analysis, you end up with some errors. So the reason I suggested this folder structure where you have your data, you've got your raw data, and then your processed outputs, is ideally your project should be laid out where you've got your raw data, any scripts that are used to clean it, these output some intermediate data files, and the intermediate data files have a different name from the original raw data. And essentially, in just one word, the main thing that I'm trying to put across here is that your analysis should be a pipeline where you can go all the way from raw data to outputs. You never overwrite your original data file, meaning when you rerun this whole pipeline, it works every time, again and again. And again, the Turing way has resources on this. They call it, research data management, and you'll be able to access those. But that's, I would say, quite a simple solution that often people don't do, but can save a lot of the headaches. Now, this make changes and reruns sounds simple, but I'll get into why this can be a challenge sometimes. So the next section I'm going to go through is how people might want to arrange their code. And what you'll notice here is I've broken it down into 2 bits. The first is custom package code, and I'll explain that in a second. And the others can be notebooks or scripts or anything more interactive. As I said, often we get this issue where data science projects grow and grow and grow. And the example on the right is actually from work that I did, where I was calculating these indicators for from household surveys. We were looking at agriculture, and in the top figure, it's difficult to see, but it's calculating something called crop harvested, and that relies on a few variables in the data set. And then at the bottom, we've got a more complicated indicator, which you can see relies on, well, hundreds of variables, many intermediate variables, and can quite quickly get complicated. The issue is with how people usually write code in these really, really long scripts, is it becomes very difficult to understand what's going on, what's working, what's not working, and quite difficult to maintain. So what I typically try to do is start off I'll explain this in a more tangible example in a second, start off with like an interactive play phase where you're exploring different functions and developing different things. Then you break down your code into smaller functions / modules. And then you find ways to test these smaller chunks of code that do very specific things. So let's see an example. On the left is, say, a typical example of a longer script. And all it's doing is calculating the mean of some data, calculating the variance and writing that to a file. And you can vaguely sort of see what's going on, but it's a little bit difficult to read. And you could imagine for more complicated examples that they're much longer, it would very quickly balloon. So what I would typically recommend people do is you break down your main analysis into smaller functions, say one function for calculating the mean, one for calculating the variance, and there's a mistake there, that should be tab indented. And then what you end up is you've got your main analysis script, which is what people will see and what you will use. And all you do is you import the functions that you find useful. You run them. So in this shorter analysis.py script, I can see that I'm importing something called mean and a function called variance, calculating the mean, calculating the variance, and writing that to a file. Whereas it's a little bit harder to see that, a little bit harder to maintain here. But the added benefit of this is that it makes it really easy to test what's going on in your code. So testing is essentially taking a small chunk of code and making sure that it does what you expect. So let's see, we've got this function that calculates the mean here. And the test would be something along the lines of, I get a test data set, like a list of the numbers 1 to 5. I calculate the mean using my mean function, that my function generates the expected result. Again, you don't have to remember all the specifics of what I'm talking about. I just want to communicate here that testing is a thing that can sometimes be used to make sure that your functions do what you expect. When do I test is something we even debate about at work. But the rule of thumb that I have is if I make a change to any code that I'm running and I'm unsure how that change is going to impact my analysis later on down the line, I usually think to myself, I probably should have written a test to make sure that that this change does what I'm expecting it to. So a number of resources that I've shared here for both Python and R, and we have the JGI, we have some materials that teach testing in the best practices for software engineering course, but that mainly focuses on Python. There are also resources that are out there to do testing in R. Again, this is something that I didn't really use at the start of my PhD, but very quickly found out I needed. And one of the things that was interesting was I found that it actually made my work much quicker, even though there's an overhead to write all this code to test all your functions. I quite quickly found I was making changes and I was more confident about the impact of those changes, so I wouldn't have to spend ages going through all my analysis line by line to make sure everything still worked, because I knew I had tests that checked that. The testing example I showed here was just for a single function, but as you would see in many of these resources, there are many tools out there that allow you to run all of your tests at once. You could test pretty much every stage in your analysis and make sure that it still does what you expect. A final thing that I'll say, because we are the Data Science Institute, I often, when I'm developing models for some of my own work, I tend to make a simulated, a fake data set and make sure that my models fit correctly to that test data set. And that also gives me a lot more confidence in any results that I'm generating, either if I'm building it into a tool or results that I'm generating for a paper. Okay, below here, and I do have an example project that if we have time at the end, I'll take you through, but if not, I'll share details of that project online so that you can look at a real code base that uses some of this stuff. But yeah, next in my list of things that I always include in a coding project is what's called an environment, or well, is essentially a file with all the software requirements that you need. So here's the scenario we often come across. You start, let's say you start one project, a particular paper, and you need packages A, B, and C. A few months later, or a year later, you start a new project, which uses some of the same packages or tools. And then you now need to go back and rerun your code for project one. How a lot of tools that install packages work usually is that they will try to install the most up-to-date version of the package you're trying to install. That's how it usually works in R. For example, on the example I'm showing on the right, is that people developing these packages might change them every couple of weeks, couple of months, or maybe once a year. And what you'll find is when you go back to the first project that originally used older versions of the packages that you wanted, that project may no longer work. So an issue we often get is this phrase that says, "but it works on my computer." And this comes from someone that's run analysis themselves, shared it with someone else, and that person is completely unable to get it to work. What virtual environments do, is you specify a file that describes everything you need to conduct a particular analysis. And you use one of these virtual environment tools that says, when I'm working in these projects, I only want to use package X version Y. And so on the example on the right, this is this isn't what an actual environment file would look like, but it's the information it could contain. So you could have an environment file that specifies the program that you're using. So for the first project, we're using R4.3 and we're using these versions of the packages. And for the second project, we're using these versions, which are different. And all these virtual environments allow you to do is to switch between these versions when you're working on your old project or your new project. I've misspelled this word. Apologies. It's been a busy couple of weeks getting this course together, but I'll send through a corrected version after this. But I generally think that you should treat the environment that you're working in as disposable, in the sense that anyone should be able to take the folder that you're working with, and using the environment file that you have, they should be able to install all of the correct packages and run your code. And these virtual environments allow you to do that. So when do I use this? Because testing I only use sometimes, particularly for larger projects. When do I use virtual environments? For every single project. It makes it really easy to manage switching between projects or work for specific papers. Here are some tools for both R and Python that you can look at, and feel free to take a picture or go back to the slides once they're shared. And I've shared some resources on some tools that you can create these virtual environments with. In particular, I'd recommend this talk on Pixie and UV. James Thomas, who's in the call, did this as a lunch and learn, and I use both of these as my primary tool for managing virtual environments now, and they're very good. And his talk helped me a lot with that. Now, last thing is quite quick, is documentation. So I usually have a folder containing documentation for each project. Documentation are different types of things that you include that explain what you're doing in your project. So you can have a few types of documentation. You can have comments in your code. So this could be within your scripts and notebooks. These should really just explain things that are not immediately obvious from looking at the code. You can have other files in your repository, like the readme file we talked about earlier. That's a form of documentation. They are designed to describe how to use the tool that you're working with. And then we can have something that's external documentation. So this could be a website for less technically minded people to understand how to use the tools or the code that you've developed. And yeah, those are just the audiences. So there are a few resources that I've shared here. Again, the Turing Way has some useful information on the what and why you might want in terms of documentation. On one of our courses, the best practices in software engineering, we've got a short section on how to use Sphinx, which is quite a common tool for generating web-based documentation. And then a tool that we often use internally on the team, but we don't have a training course on how to use that yet. But we use this thing called Quarto, which is a whole ecosystems of tools for both Python and R, but also includes the ability to create books and online documentation. Now, I've got more resources in this slide that you can go through afterwards, but I think I've spoken at you for quite some time now, so I think it'd probably be better to talk through, or to have some questions and talk through some of these concepts. But essentially, the last thing I want to say is I've shown you a lot of different things that are out there. And this was something that I wish I'd seen at the start of my PhD. I did have a class that sort of did this, but I think you don't have to use all of this stuff straight away. But as you're learning to code, I just think it's useful to have in the back of your mind that there are a lot of tools that are out there that can make working on these types of analysis projects a little bit easier. And slowly over time, piece by piece, you might want to consider trying to integrate some of these. And this PowerPoint, this presentation that we'll share afterwards, I hope is a useful summary of some of the concepts that you might want to use and that you can go back to when you decide in a year's time that you might use some testing or some documentation frameworks. And yeah, finally, just that this comic on the right, I think raises a really good point. When we're learning this sort of stuff, we have a tendency to almost over-engineer every single small project that we're working on, and it takes time to find the right balance of what's necessary and what works for you. Cool. That's all I want to say for now. There's an appendix. There's a section after this that talks about version control and some other things that you might want to look at. But yeah, I'll take some questions now, and we can chat through anything that wasn't clear.